So this is the n-dimensional Jacobian formula. We start with a random vector n cross 1, which means it consists of components x1 to xn jointly distributed, and the transforming function h from Rn to Rn. This is for the case where both the domain and the codomain has the same n, and it has to be a bijection. We assume H inverse is differentiable. We already know what is meant by multivariate differentiability. Let the result of the transformation be denoted by y, which is also a n-dimensional random vector. Now if x has density, some fx, gy, which is f of H inverse of y, times a number j, this j is the absolute value of the determinant of the Jacobian matrix of H inverse, not of H, but of H inverse, because I have assumed H inverse is differentiable. So this plays the role of that absolute value derivative, etc., that we saw for one-dimensional Jacobian formula. Now this looks pretty complicated, but once you get the hang of it, it is not much that difficult, because H inverse y is just x. So it is basically fx together with a scaling factor, much like the one-dimensional case. The scaling factor is obtained by finding the Jacobian matrix of H inverse, then taking its determinant and then working out its absolute value. In general, this is also a function of y, where you are doing it. So let us see this in an actual example. In this example, we start with x1, x2, which is uniform on this square. So if you take some observations, it could be just anywhere, any point is as likely as any other point. Now I define the transformation x1 times x2, that is called y1, and x1 is given the name y2. So given the two numbers x1, x2, I am constructing two other numbers y1, y2. So this is a transformation. These are new random variables. My job is to find the joint density of y1, y2. Now to solve it, I shall first give this a simple name. Then the joint density of x1, x2 is given by f x1, x2, which is 1. If it lies in S, remember the area of S is 1, so this is 1 by 1, 1, and it is 0 outside S. In order to apply the Jacobian formula, we need to write this transformation as a function from R2 to R2, and that is this. The first component is x1, x2, that is y1. The second component is x1, that is y2. Now this function is actually a bijection when I restrict my attention x1, x2 in S, because if I tell you x1, x2 and x1, you can always recover x1 and x2 separately. x1 is already given, and divide this quantity by x1 in order to recover x2, and division by x1 is not a problem because x1 is not 0. Now we can find out H inverse because I know it's a bijection. So if someone gives me y1 and y2, how can I recover x1? Well, x1 is same as y2, so the first component will be y2. And how do I get x1? x1 is obtained by dividing y1 by y2, so it will be y1 by y2. That is the inverse function. Now we have to compute Jacobian of this H inverse, so I take the first component, which is y2, and differentiate this with respect to the first argument y1, so I get 0. Now I take the same component, but now I differentiate it with respect to the second one, so I get 1. Partial derivative of y2 with respect to y2. Now I come to this component y1 by y2, partially differentiate with respect to y1, and you will get 1 by y2. Partially differentiate this with respect to y2, and you will get minus y1 by y2 squared. So that is our Jacobian matrix. Next we shall find the determinant, which is this times this minus this times this, which is this. Now I know that y2, which is actually x1, is positive. So when I take absolute value of that, the absolute value will not have the minus sign. So now we are in a position to write down the density of y. G of y1, y2 was f of H inverse of y1, y2. I already have it here. So it is just y2, comma y1 by y2 times this absolute Jacobian 1 by y2. That's it. Now I remember that f was identical equal to 1 if this point lies inside S and 0 outside. So I can further simplify it as G of y1, y2 will be 1 by y2 times 1. So now since the density is just 1, if my original x1 and x2 are this, y2 and y1 by y2, they lie in my S and 0 otherwise. Now you may not quite like this idea that I write it in this weird way. You would naturally prefer to write it as y1, y2 lies in some set. So the set should better be described in terms of y1, y2 rather than this complicated thing. But coming from this S to this T is just a matter of pure algebraic manipulation. The class web page gives you how you can manipulate in this particular example. In general, this may be quite complicated, but this is the actual density. It may not look very appetizing, but this is the answer. In this problem, I have given you a joint density x1 plus x2. If x1, x2 both are in the unit interval, you have to find the density of the transformed variable x1 plus x2, x1 minus x2. So this is your y1, this is your y2. Just apply the Jacobian formula and you will get it in a minute.